Data deduplication, or simply dedup, is a data optimization technique that eliminates redundant copies of data in order to reduce storage requirements. In simple terms, it ensures that only a single copy of a piece of data is stored, while any subsequent copies are replaced with pointers to the original data. The process of deduplication begins with data chunking, where the data is divided into smaller chunks, often called blocks or segments. These chunks can be of fixed size, like 4 KB, or variable size in variable length deduplication. Next, each chunk is processed using a hashing algorithm, such as MD5, SHA, or CRC32, to create a unique hash or fingerprint for that chunk. This ensures that identical chunks will have the same hash. The system then compares the hash of each new chunk with the hashes of previously stored chunks in a database or index. If a chunk's hash matches a previously stored chunk, the system doesn't store the chunk again. Instead, it stores a reference to the already existing chunk. This leads to storage optimization, where only unique chunks are stored, greatly reducing the amount of data that needs to be stored, discarding duplicates. There are different types of deduplication. File-level deduplication, also known as single-instance storage, looks at entire files and checks if an exact duplicate exists. If the file is already stored, any new copy of that file is not stored, but instead a reference to the original is created. This method is best for situations where files are mostly identical, such as backup files or documents. It is simple and easy to implement, but less efficient in environments where file contents change frequently. Block-level duplication, on the other hand, breaks files into smaller blocks and checks if individual blocks are duplicated. This method is more granular and efficient, especially in environments with many small, similar files, but it can be more complex and incur overhead for indexing and comparing blocks. Variable length deduplication dynamically determines the best way to break data into chunks of varying sizes, using a more sophisticated algorithm to detect similarities across different data patterns. This approach can be more efficient for certain types of data, but is also more computationally intensive. The benefits of data deduplication are significant. The primary benefit is storage space savings, as deduplication reduces the amount of storage space required by eliminating redundant data. It also improves backup efficiency, especially in backup environments where large amounts of redundant data are stored repeatedly. Common use cases for deduplication include backup and archiving, where it is most commonly used to reduce redundancy in traditional backup systems. Cloud storage providers also utilize deduplication to reduce storage costs and optimize data transfer. In virtualized environments, deduplication can significantly reduce storage requirements by eliminating repeated data across virtual machines. Email systems benefit from deduplication by reducing the storage overhead associated with redundant emails, while data replication and WAN optimization see advantages as only unique data is transmitted, speeding up data transfer. However, there are challenges and considerations with deduplication. Performance overhead can be a concern, as deduplication may add computational overhead, particularly when indexing data and comparing chunks. This can impact performance, especially on systems with high throughput data. The complexity of implementing deduplication, particularly at the block level or with variable lengths, can require more sophisticated infrastructure. Additionally, if the deduplication index or database is corrupted, there's a risk that pointers to deduplicated data might be lost, potentially affecting data recovery or integrity. Latency can also be an issue, especially in real-time deduplication systems, as they may experience delays while checking each piece of data for redundancy. Lastly, deduplication can sometimes cause data fragmentation, which might affect performance over time. For example, in a backup environment, a company backs up a directory with 1,000 files. Over a few weeks, only 100 of the files change, while the remaining 900 stay the same. Without deduplication, each backup would store all 1,000 files. With deduplication, the system stores only the new or changed data and references the existing data, saving substantial storage space. In cloud storage, if a user uploads files multiple times, the cloud system with deduplication would store only one copy of the file and reference it each time it is uploaded in, reducing both storage costs and bandwidth consumption. In conclusion, data deduplication is a powerful technique for optimizing storage, reducing costs, and improving backup, recovery, and data transfer processes. It is especially useful in environments like backup systems, cloud storage, virtualization, and data replication, where large amounts of redundant data are common. However, organizations must balance the benefits of storage savings with the potential performance and complexity overheads that deduplication may introduce.